All right, we are on Unit 5, Section 1, normal distribution and combining normal random variables with our sample distribution. So in this unit, we're going to be looking at, in the next section or two, we're going to be looking at finding the probability of something occurring given a normal distribution, finding that probability. So let's start off with just going over again what a normal distribution is. So if you have continuous random variables, within a specific domain, which is essentially telling you like a range of numbers from, let's say, 10 to 100, or 60 to 80, etc. But you have continuous data. It's not categorical. Okay, it's not going to be discrete. It is continuous. With these random variables, they are normally distributed based off of the population, which means it's going to occur like a bell. So it's going to be that bell curve, that normal distribution curve that we have. That's what we're going to be looking at. The area underneath this bell curve is going to be equal to 1, which means it's 100%. So if we can find the area within the range that we want to look at, being less than a number, greater than a number, or between two numbers, that area that we find will be the probability of that range of numbers occurring in this given situation. So what we're doing here is that we're trying to find the area. So there's three different ways that we can have our probabilities be bounded. The first one is that x is always less than a number. So it's always going to be the probability of x, or whatever your main variable is. And then here it is less than this x sub a is a number. So it's going to be like 60 or 30 or 150 or 0.2. This is going to be a number. Now, looking at the graph itself, it's that left-hand tail. So it's the lower tail of this bell curve that we have. That is for this type of probability. If you're between two numbers, it's going to be the number is less than x, which is less than the upper number. And so it's going to look like this. It does not need to be on both sides of the mean. It could all stay on one side of the mean. So you could be looking at, let's say your mean was 8.2. You could be looking at from 7.9 up to 8. Okay, so it can stay completely below the mean, or it could stay completely above the mean. And the last one here is that the probability of the variable is greater than some number, and that's where you have your right-hand tail looking at the upper half. So those are your three situations. When you're doing these, you do want to sketch the graph itself so that you can see exactly where your bounding is and make sure it matches up. All right, so what you need to show with these. So the basic ones right now. Soon there's going to be a 4-step process that you're going to do, but this, just to start, will be fine. Number one, we need to state what our distribution is and the values of interest, which is the mean and the standard deviation. Easy way of doing this, number one, you state what the variable is. So what does x represent? And then from there, you're going to use this n parenthesis mu sigma. So the n is going to stay there. That's telling us it's a normal distribution. Mu is the mean, and then sigma is the standard deviation. So whatever it is, you can go, oh, it's this, comma, that. The mean is 100, and the deviation is 30. So it'd be n parenthesis 100, comma 30. Perform the calculations itself. Make sure you show your work. The big thing here is identifying what the z-scores are and drawing the curve. Yes, I know that your calculator can do basically all of this on its own, but we don't want to have it all done with the calculator. We have to show some work, and that work that is shown is the z-score itself. Last part here, answer the question. So once you're able to answer the question, and remember, you want to say context for it as well. So what does that probability represent? Okay. First example here, we have the height of young women, and it closely follows a normal distribution with a mean of 64 inches and a standard deviation of 2.7 inches. This distribution is a large set of data, so because it's a large set of data, we don't really have to go through and prove certain things. Now, one woman is chosen at random, and so this is the question that's being asked. If one woman is chosen at random, what's the probability that she's going to be taller than 65 inches? What's the chances that she's going to be smaller than 65 inches? And what's the probability her height's going to be between 68 and 70 inches? Okay, so there's our range of numbers. So let's start off with the first one. which is what's the probability that she is going to be greater than 65, or her height is going to be more than 65 inches. First thing we need to do is define what the variable is and then state our normal distribution. So our variable here is the height of women. You could be more descriptive with height of women in inches if you want. It's not, doesn't need to be that picky. Next up, you say that the x value is approximately normal, because since it's a large data set, and I believe it says in the problem itself, says right here, follows a normal distribution. So it tells you that it's a normal distribution curve. Mean of 64, deviation of 2.7. Okay, so there's our values. There's us defining the variable and then stating what the normal distribution is. There's our first value. Next up after that, we're going to state what the probability we're trying to find is. So the probability we're trying to find is that x is greater than 65, which means we are going to, when we do our drawing, it'd be a normal distribution curve, and we'd be looking at that right-hand tail, so that upper limit tail, 65. Here, you do not need to put this inside the p-value, or you don't need to write p parenthesis and then the z. You could just do the z formula. So 65 minus 64, the x value minus the mean, all over the standard deviation. This is a large enough sample. This is the formula we use. We end up getting 0.37. And then from there, you can either use the table or you can use the calculator. The calculator you're using a normal CDF. 0.37 is your lower, 1e99, or 1 times 10 to the 99th is your upper limit, basically off into infinity. 0 is the mean, and 1 is a deviation when you're using the z value. Now, for your calculator, once you find this z value of 0.37, you could go and use the actual values. So you could change this 0.37 to 65. You would have to change 0 to 64, the mean, and you need to change 1 to 2.7, and you'd get essentially the same answer. Answer here, we get a probability of about 0.3557, so about 35.5%. Okay, moving on to our next part, we're looking at women that are less than 63. So same situation, our same x, our same normal distribution of 64, 2.7. So same setup here. The difference now comes into play is with our probability. So our probability ends up being that x is less than 63. Okay, so we're looking at the left-hand tail of it. So we're looking at, if you draw the normal distribution curve, we're looking at the left-hand part of it, small side of it. Again, z value stated, and if you notice with this one, the z value is negative. The reason it's negative is because it's below the mean. So it's negative 0.37. Stating our normal CDF, again, using your calculator here for this part, your normal CDF, negative 1e99. That is your absolute minimum that you're going to have, to negative 0.37, and then 0, 1. Again, this is if you're using the z value. If you're using the original values, you want to use 64 and 2.7 for these last two values, and 63 for the second value. They're going to get you the same answer, but you have to show the z value, so that's why the z value is being used here. And again, if you notice that this one is the same probability as 65. Now there's an error here. This should be less than 63, but they do come up with the exact same value. And the reason is because from the mean, they're both 1 inch above and below the mean. And since a normal distribution curve is symmetrical, if you're the same distance from the mean on either side, the distance from your point to the closer tail or the closer end is going to be equal for both sides. Kind of cool. All right, last one here is looking at from 68 to 70 inches. So we're looking at a range, and this range is completely above the mean, okay? Now, you could do some of this with the table, but again, you should be using your calculator because it is quicker, because you can just run it through real fast. And your calculator is going to be more, what do I want to say, precise. It's going to be correct more often than you would be looking at the table, you know, because sometimes if you're looking at a table, you might jump a line, something like that, and mess up. Your calculator, as long as everything's put in, your calculator's got it. So for this one, we're looking at the range from 68 to 70. Same normal distribution, same variable here of the height of the women. Our z value is going to be from 68 minus 64 all over 2.7, and then the upper side would be 70 minus 64 over 2.7. Those z values are found as 1.48 and 2.22. Using your normal CDF again, you'll be using your lower and upper bounds. Since this one doesn't go off infinite, so it's not saying it's always greater than or always less than a number, you don't need that 1e99 sitting there, or 1 times 10 to the 99th is what that e stands for. Your normal CDF, again, you can change out the 0 and 1 and use the original values. You would just need to use 68 and 70 instead of 1.48 and 2.2 repeating. And the probability here is about 0.056 or 5.6%. So you see, if you pick somebody at random or you pick a woman at random, there's about a 5.5% chance that they would be between 5'8" and 5'10". All right, that's the end of this section. Okay, we're going to continue on looking at more with probabilities moving forward and doing our 4-step solutions.